Hey class, in this video I'm going to go over a couple of examples for how to balance a chemical equation and then some tips and tricks for how to make the job a little bit easier. So, I've got an unbalanced chemical equation right here. We can tell it's unbalanced because I do not have any coefficients present. What balancing a chemical equation is for is to observe the law of conservation of mass. That basically tells us that all of the atoms on my left side of my arrow, on my reactant side, have to exist on my right side of my equation, my product side. The law of conservation of mass tells us that mass cannot be created or destroyed. So if I've got some atoms working on the left side of my equation, they have to exist on the right side of my equation, and vice versa. Things can't just come out of nowhere, they can't disappear, and they can't appear from nowhere. So that's the point for balancing chemical equations. How that's done is by adding our coefficients to each one of our substance quantities to show each atom moving from our reactant side to our product side. So in this chemical equation, we've got ethane, C2H6, it's called ethane, plus molecular oxygen, O2, yields carbon dioxide, CO2, and water, H2O. So to start, I'm going to split up my product side from my reactant side. And the first step is to tally up all of the atoms on each side of the equation when it's unbalanced. So, first thing I need to do is identify what atoms, what elements I've got. I've got carbon, I've got hydrogen, and I've got oxygen. And what that should mean is that I've also got those exact same ones on the other side. I've got carbon, I've got hydrogen, and I've got oxygen. I've got oxygen in two places, which is important. So I've got to account for both oxygens in my total tally. I've got 2 oxygen in carbon dioxide, and I've got 1 oxygen atom in my water molecule. So if I do a tally, I've got 2 carbon on my reactant side. I've got 6 hydrogen on my reactant side, and I've got 2 oxygen on my reactant side. This is because I've got 2 carbon atoms in 1 ethane molecule from the subscript 2. Same thing for hydrogen with the 6, and then same thing for my oxygen with the 2 right here. If I were to do the same thing on the left side, CHO, I've got 1 carbon on this side. There's no subscript there, so it's a 1. I've got 2 hydrogen, 2. And then I've got 3 oxygen. I've got 2 oxygen in my carbon dioxide, and I've got 1 oxygen in my water molecule. So I've got 3 here. So we can see that none of our quantities are matched up at all. I've got more carbon atoms on my reactant side, I've got more hydrogen atoms on my reactant side, and then I've got more oxygen atoms on my product side. So I've got to add some coefficients to make sure that the total amount of atoms on my reactant side are reacting with the total amount of, are reacting and becoming the total amount of atoms on my product side. So I do that again by adding coefficients to these quantities. It's going to be an iterative process. We're going to put in some numbers that we're going to have to erase. So the first place to start, we see that we've got, sometimes it's good to start just from the top. I see that I've got, actually one thing first. So because we've got 2 molecules with oxygen on this side, and we've only got 1 molecule with oxygen on this side, our last one is going to just be adjusting this oxygen to account for these. Because oxygen is by itself right here, so we can just adjust oxygen at the end to match whatever we got here. But whatever we put in here for oxygen, it's going to be an even number. Because our coefficients have to be whole numbers. So we can't put in like 1.5 or 2.5 here. They have to be whole numbers. And so anything times 2 is going to be an even number. That's not the case over here. We could end up with, and actually we do end up unbalanced with an odd number of oxygen. We know right away we're going to have to change our amount of oxygen, and it's going to have to be even, because our quantity of oxygen is always going to be even on our reactant side. So we know we're going to have to do some work there to start. But we can start with adjusting our carbon dioxide quantity first. And we see that we're going to have 2. We can throw a 2 in there. And what I'm going to do is I'm going to use a pen, because it's going to be a little bit easier. I'm hoping this shows up well on camera. 2. That looks fine. We're going to have a 2 there for carbon dioxide, and that's going to change. Basically what this thing is, now we've got 2 entire molecules of carbon dioxide. So in each molecule, I've got 1 carbon and 2 oxygen, but now I've got 2 of those molecules. Just like you distribute in a parentheses in math class, we've got to distribute this 2 to carbon. So 2 times 1, that there should be, like, we can assume there's a 1 for the subscript for carbon. 2 times 1 is going to be 2, so I'm going to put a 2 in there. And then I've got to do 2 times 2 here. So I've got 4 total oxygen atoms. Coming from carbon dioxide, I've still got that 1 coming from water though. So in oxygen, this goes from 3 to 5. We're still odd, so we still got to do some work for oxygen. But we've adjusted that now, and now our carbon are good. Next, we can go down. Carbon is good, we've got 2 and 2. Hydrogen, we've got 6. We've only got 2 hydrogen on this side. But it's all coming from 1 quantity, from 1 substance. So if we threw a 3 in there, because we've got 2 and our target is 6, we can put a 3 in, and we can say that 3 is going to change our total hydrogen count from 2 to 6. Because we've got to multiply that 3. We've got 3 molecules of water now. Each molecule of water has got 2 hydrogen atoms. So now I've got 3 water molecules. So I've got 6 total hydrogen atoms. It goes 3 times 2 for a total of 6. And then I've got to do the same thing. I've got to multiply that 3 by the 1 there for my oxygen. Oxygen doesn't have a subscript, so it goes 3 times 1. Remember, we've still got these 4 over here. Now I've got 3 over here. So it gives me a total of 7. So my carbon are matched up from before. My hydrogen are now matched up. But now my oxygen aren't. I've got 2 and I've got 7. So, as I mentioned before, it's great if we just have oxygen to match up, because I can just control this side. I can just adjust this coefficient right here, and I can make oxygen equal that. But we're running into our problem that I mentioned earlier. I want to get the number of oxygen atoms on my reactant side to equal 7. I can't do that. If I multiply this by 2, I'm at 4. If I multiply it by 3, I'm at 6. If I multiply it by 4, I'm at 8. There's nothing I can do to get me to 7 oxygen atoms, because I've got an even quantity here, so anything I multiply it by is still going to be even. One of my tricks, and the book tells you to do this trick a little earlier, but I like saving it till the very end because it makes things really easy. If all you have left is to adjust one quantity, one molecule, and you need to get to a number that it can't, you need to get it to an odd number, put in the fraction, or I should say, put in the decimal you need to get it to 7. So if I want to get 2 to 7, I've got to multiply by 3.5 to make it a balanced chemical equation. We can't do that. That's a little wrong right now, but we're going to see what happens. So 2, now I've got 3.5 oxygen atoms. That would put me at 7. And now this equation is balanced. But we can't have this 3.5 in here. what we can do, once you get to this point, once we're balanced with a non-whole number, we can just multiply everything by 2 to get it all whole. Multiply every coefficient by 2, and this will still be balanced, and we'll get rid of this 3.5. So, to do that, I need a coefficient of... So, what I'm going to do basically is I'm going to multiply each coefficient by 2. I'm going to double everything. Everything's going to stay balanced. It's like when you multiply both parts of a math equation by 2. The equation is still valid, but we're going to get rid of this 3.5. It's going to become a whole number. So I've got a coefficient of 1 right here. I don't have a coefficient, so it's assumed to be a 1, just like for subscripts. So I'm going to put a 2 in right there. This 3.5, the whole reason we're doing this is to double this and make this a 7. I've got a 2 here in front of carbon dioxide. I'm going to make that a 4, doubling that 2 to make it a 4. I've got a 3 here in front of water. I'm going to double that, make it a 6. So now I've got to readjust the counts of each individual atom. So I doubled my ethane. So now I've got 2 molecules of ethane that each have 2 carbon atoms. So this becomes a 4. Same thing for hydrogen. I've doubled it. Each one has 6. So this becomes a 12. I've doubled my oxygen. So instead of being multiplied by 3.5 to get 7, I'm multiplying by 7 to get 14. So I'm going to do the same thing on this side. I've got a 4 in front of my carbon dioxide. Each carbon dioxide only has 1, so I'm going to change this count to a 4. Oxygen has 8, so I'm going to change this to an 8, but I know I got a couple over here that I've got to deal with, so I'm just going to put a plus there, because I know I'm not done there yet. Then I've got a coefficient of 6 in front of my water. 6, I know each water molecule has 2. My coefficient is 6, so it's 6 times 2, which is 12. And I've got those 6. The 6 in front also affects this oxygen atom on the end. There's a coefficient of 1, so I know it's 8 plus 6, which is 14. 4, 12, 14. 4, 12, 14. My law of conservation of mass is observed here, and this becomes a balanced equation. So I've got a coefficient of 2, a coefficient of 7, a coefficient of 4, and a coefficient of 6. That gives me carbon that's balanced, hydrogen that's balanced, and oxygen that's balanced. All of the atoms on my reactant side exist on my product side. No mass has been created or destroyed, so we can say that this is balanced. And one last thing, what this means is that it takes 2 molecules of ethane and 7 molecules of molecular oxygen to yield 4 molecules of carbon dioxide and 6 molecules of water. It takes that amount of each one of these molecules to complete this reaction. So 2 molecules of ethane react with 7 molecules of oxygen to yield 4 molecules of carbon dioxide and 6 molecules of water. That's what these coefficients mean. When it's balanced, this is how the reaction works in real life.